All right. So it mentioned that I work to make little computers, and in a tragic sense of a little bit of irony here, I suffered a hard drive failure on my way here to Chicago. So the presentation isn't going to be quite as flashy as it normally would have been, but we're going to work with what we got. So just by a show of hands, who here remembers their first computer? We got just about everybody in the room. That's awesome. Now, how many of you that remember that it was probably susceptible to the Y2K bug? Yeah? Now, I remember my first computer. My dad brought it home, took it out of the box, and set it on this nice wooden desk. I was really young, probably about 3 or so, and I was really confused because the first thing I saw when he plopped it on the desk was a thing that looked kind of like a TV. But it wasn't a TV because it didn't have any of the buttons, dials, or knobs that changed the channels because we didn't have remote controls back then. And then it had this other weird attachment thing to it. It had this big beige box with a large rubber black button on it that when you pressed it went ka-chunk. And as things started whirring up on the inside, there was a black and green LED that shone the number 42 above it. I never figured out what that number actually meant. And at the time, I had no absolute concept of what that one machine would turn into as far as my life was concerned. My dad bought it probably for some grown-up purpose, like taxes or whatever. It certainly wasn't browsing the internet because it was actually before the internet became available to the public. So the development of computers over the past 50 years has grown absolutely exponentially. And I use that word literally. Over the course of 2 years, the processor size inside a computer will double. And that has gone on since Gordon Moore predicted that back in the 1960s. Here I show you a picture of a hard drive in 1956. That hard drive is 5 megabytes. It had to fit on a plane! 5 megabytes. Now you think about that in modern terms, 5 megabytes is about the size of 2 pictures raw on your cell phone. It wouldn't even fit, a full website page on there. Just too little memory. But as we've gotten better at making computers, as we've gotten better at making memory and the components, they've gotten smaller. And as they've gotten smaller, they've gotten more efficient, they've gotten faster, and that's led us to create better and better devices for us to use. And as my friend Buzz here can attest, we are surrounded by circuitry. Our cell phones, the projector, this computer, this device thingy with a laser in it. I mean, they have gotten to become so efficient that we just don't notice them anymore. And that's a great thing. Now, I work in molecular electronics. This is taking the advances that we've been able to achieve over the past half century or so and bring it to an entirely new realm. But how do we do that? Why do we do that? We do what we do so that we can make improvements to our different lives. Now, molecular circuitry would ultimately, in an ideal sense, be smaller, faster, and more efficient. More efficient, yes! Faster, absolutely! Smaller, why? Aren't things small enough? I would say not really, and this is where we're bringing the nanobots into it. We're going to say that, hey, if we're going to advance medicine, if we're going to advance our technology, we need to make sure that we can get smaller. But how do we do all of these things? How do we actually know what it is that we're creating? Well, in my research, I start by using a really big computer, ironically, to design what's ultimately going to become really tiny computers. I know, it doesn't get past me. And so I feed models into this supercomputer to calculate different attributes that I want about the molecules that I need. geometry, energy, these sorts of things that allow me to figure out, okay, how are electrons going to be affected inside, inside my system? And then when I get the data out, I interpret it and decide what kind of molecules it is that I actually want to make. But then I actually go into my lab and make them. And this is the cool thing about the intersection of molecular materials with chemistry and physics, is I get to do the modeling, and at the same time, I go in the lab and make molecules that nobody's ever made before. Nobody's ever seen them. You know, we can think about them, say that they're probably possible, but when it comes down to it, going into the lab, saying, oh, hey, I got this molecule, here's the proof. Here's a nice, pretty little crystal. That's the real power behind the chemistry that's coming out. And then, once I figure out and actually make the molecules, then I can assemble them into the device and go ahead and test my hypothesis. So what we do is we take my molecules, and these aren't actually my molecules, but they're a nice little substitute, and we put them into a solution onto an atomically flat gold surface. Atomically flat. It's the flattest thing you can ever get. And from there, we can let them self-assemble. We can use the molecular properties that we designed and built into the molecules so that they arrange themselves in a regular format along the surface. And once we have that arrangement, we can top that with another metal electrode so that we can bring a full circuit together, and we can pump the electricity through it. Now, my molecules are designed to be molecular diodes. And for those of you that aren't electrical engineers, diodes control the efficiency and flow of electricity in one direction in a circuit. You would know them as the D in the LEDs that you would have in your light bulbs or the lights, the screens for your phones. And so what we can do with these molecular machines is project a little bit into the future about how we want to start making actual mechanical systems, not just strictly electrical. And so I use this as an example. James Tour out of Rice University in 2010 made a molecular Nano Car. His group synthesized this molecule, and when they added electricity to the surface, these balls on the end of the molecule rolled along the surface and rolled in a controlled direction. It wasn't just some random movement skittering about on the surface. It moved forward. And they proved this because then they synthesized some other shapes where the wheels weren't straight forward. And it turned. And it turned in the radius that you would predict for a molecule of that size and the geometry that they made. So they made something that could roll around. And since then, molecular motors have been made, molecular cars, shuttles, little globules that are going to deliver medicine into cancer cells and things of that nature are getting to be really, really important. And while these are interesting intellectual ideas, being able to bring them into something that's useful is the real power behind the science. And this year, I was just reading the ACS Nano magazine, and a couple of researchers actually were able to create a device that, when you blow into it, would detect ovarian cancer. And that's just like, what? A straw. And that was the key point, is it was a flexible sensor substrate, basically like a straw that you blow into, and it tells you if you're susceptible to ovarian cancer. And that's huge. That's absolutely powerful. And so while we're surrounded by all these nifty, great gadgets, the ability to affect the health and happiness of our loved ones, that's the real superpower of nanotechnology. Thank you.